And welcome back, friends, to Cajun Coding. We are still on Codingbat in the Java language, and we're about to embark on the Logic2 series of problems. These are problems that are becoming a little bit more complex. Now, we're getting away from introducing the syntax of the Java language and getting more into more complex problem solving. So, it's a two-edged sword. On the bad news, if you want to call it that, is that these are more difficult. They're more challenging. It's harder to find a solution to these simply because of the complexity of the problems, the way they're framed. Now, the good news is that most of the difficulty is not coming from the syntax of the language itself, but from properly framing and breaking down the problem to develop a solution. So the solution to these problems is really language agnostic. If you can solve these problems in Java, you can probably solve them in any other language that you know, or even in a language that you're not familiar with after you've been introduced properly to the syntax and conventions of that language. And this is really where we're getting into good practice with the language that you're using. Putting the tools to work, you're getting beyond the point at which you're just being introduced to the tools and how they work. So you're looking at the problem. The mark of a master craftsman in any trade, whether you're using physical tools or cognitive tools like programming languages, is that the tools become invisible. You're not paying attention to the tools, you're paying attention to the problem and the task at hand. So let's go ahead and get started. The first problem here is make bricks. And I've encountered this problem a few times. I'm not sure if it's as popular as FizzBuzz, but it is interesting. An interesting problem. It's a bit more complicated than FizzBuzz, as you'll see. We want to make a row of bricks that is goal inches long. We have a number of small bricks, 1 inch each, and big bricks, 5 inches each. Return true if it is possible to make the goal by choosing from the given bricks. This is a little harder than it looks and can be done without any loops. Okay, now I find the best strategy to go with this one, or I found the best strategy. I don't know if it's the best, but it worked better for me. Sometimes you have to flip a problem around rather than try to figure out the situation in which it's possible. We can specify conditions which make it impossible. And if we've done all of those, then we can default to returning true and stating that it is possible. So sometimes it's easier to flip the logic there. So we're going to go ahead and start with this if statement. If all the bricks put together fall short of the goal, then obviously you cannot accomplish the task. So if big, and they are 5 inches long each, so if big times 5 plus small is less than goal, then we return false. That part's pretty easy. And we're going to check another condition which would make it impossible. Let me see. So if we do goal modulo 5, what that's going to do is that's going to find out how many small bricks we are going to need. Goal modulo 5. So we're dividing the total amount. We're actually not dividing the total amount. We're finding modulo. So we're dividing, but we're just taking the remainder, remember. So we are definitely going to need at least goal modulo 5 small bricks. Because if we don't have that, say we have no small bricks and the goal is 17, well, 3 bricks is 15, 4 is 20. If we don't have those small bricks to make that exact number, it's impossible. So if goal modulo 5 is greater than the number of small bricks we have, then that is also going to be impossible for us to accomplish the task. So we also return false. And our default would be return true. Now you say here, well, what if we have very few big bricks? You know, then we would need a whole bunch of small ones. Except we already checked up here that the total amount of bricks we have exceeds or at least equals the goal. And I promise you, I did not solve this quickly the first time I did this problem. Far from it. This is one of the problems that I might have gotten stuck on for a really long time. It's the exact kind of problem that I ran into that I felt, you know what, if I stay stuck on this for 3 days, I do not feel that I'm going to learn as much as if I find a solution, quote unquote cheat, but then once you find that solution, study it. Study it, pick it apart, make sure you understand why that's the solution, and then get back on track and continue to study and do other problems and such. So, and that's kind of why I'm making this series here. So that's make bricks. There are other solutions out there, but this one is the most succinct. And once you really look at it, it's not real hard to understand. So, next exercise: lone sum. Given 3 integer values, a, b, c, return their sum. However, if one of the values is the same as another of the values, it does not count towards the sum. So we're going to be adding these values up, but there's conditions on whether we're going to be adding them up. So let's go ahead and rather than just coding this so it's just one line, which I'm not even sure is possible, let's go ahead and set up our sum, and we're going to go ahead and set it to 0 initially. And now if we're going to put a, if a is not equal to b and a is not equal to c, then we're going to add it, sum plus equals a. And essentially, we're just going to do this 2 more times. Except we're going to use b here. And we're going to use c here. And then we return sum. And I think this is very closely mirrors their solution. It's actually virtually identical. The first time I did this, actually it was kind of weird the first time I did it. I'll go ahead and show you what I did here. If a equals b and b equals c, if they're all the same, none of them count, so we just return 0. Actually, I set sum a plus b plus c. Now once we set sum there, we're going to return 0 if they're all the same. So it doesn't matter what we set sum to. Okay. And then what I did was, if a equals b, take sum, and then we subtract from sum a times 2. Then if b equals c, sum minus equals think I need to do one more. If C equals A, that's the one we missed. It's a little bit more verbose, and it's a little harder to see what's going on here. But what we do is we sum all three. If they all are the same, then we just return a 0. And under the else block here, if A equals B, B equals C, or C equals A, what we do is we remove both of those from the sum. So I don't recommend this solution. I just wanted to share it with you guys just to so you could see that there's different ways to go about doing these things. If you get a career in coding and you're reviewing code, you'll definitely see some code out there and you're thinking, this is not efficient. This isn't the way. Why on earth would someone have done this? And I promise sooner or later it's going to start looking familiar and you're going to realize you're the one that wrote the code. So maybe first lines of code you wrote before you got coffee, maybe it's the last ones you wrote after a 10-hour day, or maybe just something you did a few years prior and you weren't equipped with all the tools and flexibility of the language in question. So, and on to the next one, lucky sum. Given 3 int values, A, B, C, return their sum. However, if one of the values is 13, then it does not count towards the sum, and values to its right do not count. And see, values to its right, I assume it's just the ones that are passed in later. This isn't an array they're passing in. They're passing in 3 ints. But let's go ahead and check that out. Let me see. So let's go ahead and set up the sum. And sum is going to be initialized at 0. And if A is not equal to 13, then we're going to add to sum A. I think the easiest way would just be to copy this. We're going to use B here and C. And let me see. And then we return sum at the end. And there we go. All correct. Now, all this do not count towards the sum if it's 13, and values to its right do not count. And all we're doing here is if it's not 13, we add. If it is 13, then we're going to return sum. If we return sum here, none of this code runs. If we return it here, this doesn't run. So we're just using the compiler instead of having to deal with this code. Now this is completely broken. This format of these series of if statements completely broken if we don't place them in the order that we received them. If we were to put C up here and A down here, this code doesn't work. So, and on to no teen sum. Given 3 int values A, B, C, return their sum. However, if any of the values is a teen in the range 13 to 19 inclusive, then that value counts as 0, except 15 and 16 do not count as teens. Write a separate helper, public int fixed teen, that takes in an int value and returns that value fixed for the teen rule. In this way, you avoid repeating the teen code 3 times. So remember, we try to keep the code dry. DRY, don't repeat yourself. And what we're going to do here is we're going to create another function. Now, all of these exercises we've been doing are functions. And I've gone through some of this stuff before. Public is an access keyword. There are also private and protected functions. We don't need to worry about that right now. But integer is the return type of the function. The name of the function, no teen sum here. Inside the parentheses are the parameters that we pass into the function, or arguments that we pass into the function. Each of those has a name here, A, B, and C, and each has a data type, which in this case is the same. The integers for all 3 of these. But what we're doing is we've been doing these functions, but we're going to be creating another function within this function, just so that we don't have to repeat ourselves here. And we're going to place that function below. Actually, they want the same indent. Yeah, same indent level as the main no teen sum. So this is going to be a public function, and it's going to return an integer. And do they want us to? Is there? Okay, fix teen. Okay, I was wondering if we were just going to name it ourselves, or okay, fix teen is going to take in an integer, and we'll just call it in. And that's our function. Doesn't have anything in it yet, and that's really the meat of the problem there. So the meat of the problem here, let me see, we're going to return their sum, A, B, and C, but with some exceptions there. So if, let me see, okay, so we're going to return the same number unless it is in those prohibited numbers. For example, so if n is greater than or equal to 13 and less than or equal to, see, well, actually there's only a few prohibited numbers. We could actually do it this way. So if n is equal to, see, 13 or n is equal to 14, n actually 15 we use 15. So if n is equal to 15, 16, so 17 or and this is just a series of numbers. Now these are not going to be added, so return 0. If it's any other number, then we just return the number. Okay, and inside our main function here, actually technically this isn't a main function, but that's, we'll get into that maybe later. Inside our no teen sum function, what we're going to do is return, and we're going to call fix teen, and we're going to pass in the value A, and then we're going to add fix teen, pass in B, and then we're going to then the process is called calling a function, or invoking. Invoking's a little fancy. We're going to call fix teen on C, and I think that should do it. I'm not sure about some of these braces there. Yeah, some of these braces are wrong, I think. Okay, so this is mated with that. This there. Here. equal start of expression. How do we do it? And all this white space, the way it's indented, 16, A, 16, B, 16, C, didn't misspell anything. But this is not a logic problem. This is a that shouldn't be it. Oops. Okay. Oh, I think I know what it is. Here it is. Okay, if you grab this closing brace, this brace is the closing brace for this brace, which is opening. But this function that we just created is a different function. So actually we should be closing here. And this function is not inside this function. It's a separate function. So I think we've got one too many braces here. There it is. See, so this is a function. We're calling this function from within this function, but the second function, 16, is not enclosed within the no_teen_sum function. So there we go, and the logic works there. And there could be, you could use a greater than or greater than or equal to, less than or equal to for some of these values here. It might knock off a few characters there, but given that there are only 5 forbidden values for adding to the sum there. Okay, so on to the next one, round sum. For this problem, we will round an integer value up to the next multiple of 10 if its rightmost digit is 5 or more. So 15 rounds up to 20. Alternately, round down to the previous multiple of 10 if its rightmost digit is less than 5. So 12 rounds down to 10. Given 3 integers a, b, c, return the sum of their rounded values. To avoid code repetition, write a separate helper, public int rounds 10 int num, and call it 3 times. Write the helper entirely below and at the same indent level as round sum. So our helper function here, we're not putting it here, we're putting it down here so I don't make the same mistake again. So here we're going to put our helper function, and let me see, what is this? Public int round 10, and that is going to take in an integer, and then we've got our braces within which we put the logic of our function. Now there are 2 possibilities when we take in a number. When we take in a number, the number in the ones place is either going to be 5 or larger, or I would say larger than 4, or it's going to be smaller than 4. Okay, now the ones place, now what's that going to be? That's going to be num modulo 10, and that'll get us the number in the ones place. Num modulo 10. If it's greater than 4, actually I should say less than. Less than 5. Okay, less than 5, so 4 or smaller. Now what we're going to do is we're going to round it down. And the way we're going to do that is, my impulse is to say we're going to exploit a feature of integer division. It's not really exploitation, it's just, it is what it is, right? So if we take a number and we divide it by 10, and then we multiply it by 10, we're returning this, by the way. Well, we would get the same number, right? Well, in normal mathematics, yes, but in the case of integer division, you actually don't get the same number. Say we're passing in 12. If we take 12 and divide it by 10, by integer division, everything after the ones place is discarded. So with integer division, what we're doing is we're taking 12 divided by 10 as 1, and then we take 1 and multiply it by 10, we get 10. So this expression here is going to discard the ones place. So that's the rounding down. If we have 5 or higher for the ones place, what we're going to do is we're going to do num divided by 10, and then we're going to add 1 to that. And our enclosures become important here. And then we multiply the result by 10. So let's say we have 15. 15 divided by 10 is 1, plus 1 is 2, times 10 is 20. Okay, now these are the only two possibilities, so we don't need a return statement down here. We've got it, the return if this evaluates to true, and the return if it evaluates to false. And what we've got here, we're just summing these, right? So we're going to return, and our name of our function is round10, and we're going to call that on A, B, C. That should be it. Yep, there it goes. And then their solution, I'm sure, is, well, they use some placeholders for the values. Int remainder. They use some. We didn't use those placeholders. Those placeholder variables, we just put the logic, right in there with the statement. And don't think that you want to avoid those placeholders at all costs. That's not the case. These are pretty simple exercises. If there's question about whether the logic is going to get convoluted enough that placeholders would be variable, are on the side of creating them rather than not. But in exercises like this, it's simple enough that I don't think it's strictly necessary. CloseFar, I think we can do one more. I think these are a little bit more complicated, but we'll do one more, and then we'll go ahead and wrap up the video and grab the next one. On the next go through, keeping the videos around 30 minutes. I'm not sure if I might make them longer later, but we'll see. Given three ints, A, B, C, return true if one of B or C is close, differing from A by at most one, while the other is far, differing from both other values by 2 or more. Note math absolute number computes the absolute value of a number. So, how to do this? Sometimes you end up with very, very simple logic in one area, but it complicates things in another area. But if we do, let me see, we can do int small, int medium, int big, and now we assign these. So if math min AB. So if the smaller of those is bigger than C, then we're going to make, then obviously C is the smallest, so we're going to make C small. Otherwise, small is going to be set to math min A B. So that's how we're going to get small. Oops, math, the math object is capitalized. Math max A B is smaller than C, and you see the logic here is pretty much the same. So obviously C would be the biggest in that case, so big is going to be C, else big is going to be the larger of math max A B. Okay, and let's see, how do we get the middle one here? Okay, so if medium so if small equals A, we need to figure out which one of these is not. No, I think I'm going down the wrong rabbit hole here. Okay, so let's do it this way. So if A is greater than small and A is less than big, because we already assigned small and big, A is going to be assigned excuse me, medium is going to be assigned the value of A. Else if B is bigger than small and B is less than big, medium is going to be assigned the value of B, else medium is going to be C. Okay, so, and that might be a little more verbose than we need. I wonder if they give a solution for this one. However, we've pretty much done all the work because this is a very simple statement here. So return math absolute difference between A small and medium is less than or equal to 1, and math absolute difference between medium and large is greater than or equal to 2. And it's long, but it's pretty simple to see what it's saying here. What is it saying? What it's saying here is that the difference between the first two, and these are ranked in order from smallest to largest here, the difference between the first two is less than or equal to 1. The difference between the bigger two is greater than or equal to 2. Or, alternately, the difference between the first two is greater than or equal to 2, and the difference between the larger 2 is less than or equal to 1. So I think that should do it. Symbol large, what's 24? Oh, it's not large, we used big. Huge difference. Big. Big. Okay, see, and that works. And they don't give an answer. What's all this? There's got to be a more succinct way to do this. This is a pretty good naive solution, though. Go run through one time. And it looks like we're about 35 minutes in, so we're going to go ahead and wrap this video up. I think we got the 3 left. So, and I'm not sure how much harder these are. I think make chocolate is similar to make bricks, but I've heard that one was harder, but I'm not sure. I don't recall exactly what it was like. So, and I'm not sure how fleshed out blackjack is. Oh, that doesn't look too hard. No, that's not too bad. I mean, as I've written whole blackjack apps with the random number generation and everything, you know. So, but we'll get on those for the next video. As always, thanks so much for tuning in to Cajun Coding, and always appreciate you guys. Comment, like, subscribe. Any requests or questions, I'd be glad to see them. And I'll catch you guys next time. Bye bye.